Somewhere over the warm Atlantic, the ocean is breathing. Water heated by weeks of tropical sun begins its transformation into something massive. The air above rises, invisible fingers reaching toward space. This is how it starts. Not with fury, not with violence, but with warmth. What follows is one of nature's most powerful creations. Yet, most people have never understood what hurricanes really are. They're not enemies. They're not disasters waiting to happen. They're Earth's solution to a physics problem, elegant and ancient, spinning across water according to rules that existed before the first human ever looked up at storm clouds and felt afraid. Before we begin this journey together, if you enjoy these quiet explorations of science, please hit that like button and subscribe to the channel so you don't miss more amazing stories tomorrow. And I'd love to know where you're watching from and what time it is there. Drop a comment below. It helps us build this community of curious minds seeking peaceful rest. Now, let's talk about how hurricanes are born. It starts with something you could touch: warm ocean water, the kind that feels like bath water against your skin. Somewhere in the tropics, the sun has been heating the sea for weeks, day after day. The water climbs past 80 degrees Fahrenheit. That number matters. Below 80 degrees, nothing happens. Above it, everything begins. The warm water heats the air directly above it. Warm air is lighter than cool air. It's full of tiny water molecules that have evaporated from the ocean's surface. This air rises, not quickly, not violently, just steadily upward, like smoke from a candle. As that warm air rises, cooler air rushes in sideways to take its place. This is wind, the very first breath of what might become a hurricane. But we're not there yet. Right now, it's just air moving over water. A process happening in thousands of places across Earth's oceans every single day. The rising air carries water vapor high into the atmosphere. Up there, miles above the ocean, the air is cold. The water vapor cools down and turns back into liquid. This is condensation, the same thing that happens on a cold glass of water on a summer day. When water vapor condenses, it releases heat. This is important. This heat warms the surrounding air, making it rise even faster. Now, something beautiful starts happening. More air rushes in below. More warmth rises. More condensation releases more heat. The system feeds itself, air spiraling inward at the surface, rising in the center, cooling and sinking at the edges. A cycle that grows stronger each hour. This can continue for days, the system organizing itself. Winds picking up gradually, clouds forming in spiral bands. What started as simple warmth over water becomes a tropical depression, then a tropical storm. And if conditions stay perfect, if the ocean remains warm and the upper atmosphere stays calm, it becomes a hurricane. But here's what matters most. This process takes time. Hurricanes don't appear suddenly. They're not born in violence. They grow slowly, methodically, following rules set by physics and thermodynamics. The ocean gives its heat. The atmosphere receives it. Energy transfers from one place to another, creating something vast and organized. It's one of nature's most patient transformations, and it's happening somewhere right now. As the storm grows stronger, something remarkable happens at its center. A space opens up. A pocket of absolute calm forms right in the middle of all that spinning wind and rain. This is the eye of the hurricane, and it's one of nature's most surprising places. Picture this. You're standing inside a hurricane's eye. Above you, blue sky, actual sunlight breaking through clouds. Around you, a wall of towering clouds spinning in every direction. But where you stand, the wind has stopped completely. The air is still. Sometimes the ocean beneath becomes smooth as glass. Birds fly here. They rest in this calm center, traveling with the storm for hours or even days. The eye forms because of how hurricanes spin. As winds circle faster and faster around the center, they create outward force, like water spinning in a bucket. The fastest winds push away from the middle, leaving empty space. This space can be 20 miles wide, sometimes 40 miles across. A circular room of peace surrounded by walls of wind. Inside the eye, air pressure drops to its lowest point. The atmosphere weighs less here than anywhere else in the storm. This low pressure is what keeps the entire hurricane organized. It's the anchor point. Everything else spirals around it. The eye's walls are made of the storm's most powerful winds and heaviest rain. These walls can tower 10 miles high into the atmosphere. They're thick bands of clouds moving in a tight circle. The contrast is stunning. Step outside the eye, and winds reach over 100 miles per hour. Step back inside, and everything goes quiet. But here's something most people don't know. The eye is warm, warmer than the air around it. As air sinks down through the center of the hurricane, it compresses. Compression creates heat. So while the rest of the storm is cool with rain, the eye stays dry and several degrees warmer. It's a warm, calm bubble in the middle of chaos. When a hurricane makes landfall, the eye passes over like a brief intermission. First come the leading winds and rain. Then suddenly, everything stops. The sky clears. People step outside, confused by the sudden peace. But this is temporary. The eye moves on, and the backside of the storm arrives with equal force. The calm is real, but it's traveling. It doesn't stay. Meteorologists use the eye to measure hurricane strength. A clear, well-defined eye means the storm is organized and powerful. A cloudy or irregular eye suggests the hurricane is weakening or struggling to maintain its structure. The eye tells the story of the storm's health. Satellites photograph hurricane eyes from space. They look like perfect circles cut into spiral clouds. Some eyes are so clear you can see the ocean surface below. Others are filled with thin clouds, creating a dome over the center. Each one is slightly different, shaped by the unique conditions of its storm. The eye proves something important about nature. Even in the most powerful systems, there are spaces of perfect calm. Order exists within apparent disorder. The hurricane isn't random violence. It's organized energy, and at its heart sits the quietest place in the entire system. That peaceful eye sits at the center of something enormous. Hurricanes are among the largest weather systems on Earth. From edge to edge, a typical hurricane spans 300 miles. Some reach 600 miles across. That's wider than the entire state of Texas. To understand this scale, imagine standing in Miami. A hurricane centered there would reach past Orlando to the north and beyond Key West to the south. Its outer rain bands would touch both coasts of Florida simultaneously. One storm covering an entire state. From space, astronauts see hurricanes as massive white spirals dominating the ocean. They're so large that Earth's curvature becomes visible in photographs, with hurricanes in the frame. These storms occupy significant portions of the Atlantic or Pacific. They're not weather events, they're atmospheric features big enough to appear on maps of the planet. But here's the fascinating part. Despite their size, hurricanes move slowly. Most travel between 10 and 20 miles per hour. That's the speed of a bicycle, something as vast as a small country crawling across the ocean at cycling pace. This slow movement comes from the steering currents in the atmosphere. Hurricanes don't power themselves across the water. They're pushed by prevailing winds high in the atmosphere. These winds flow like rivers of air, carrying weather systems along defined paths. The hurricane rides these currents like a leaf on a stream. Near the equator, trade winds push storms westward. As hurricanes move north, they encounter different wind patterns. Around 30 degrees latitude, the westerlies take over, steering storms back toward the east. This creates the classic hurricane path. West across the Atlantic, then curving north and east in a long arc. The journey takes days. A hurricane forming off the coast of Africa might take 2 weeks to cross the Atlantic. It travels thousands of miles at that steady bicycle speed, growing or shrinking depending on ocean temperatures below and wind patterns above. This slow movement gives us time. Time to watch, time to prepare, time to evacuate if needed. Hurricanes don't surprise us anymore. We track them from birth to death, watching their every move with satellites and weather stations. The size also means hurricanes affect huge areas for extended periods. A single storm might bring rain to coastal regions for 3 straight days as it passes. The wind field extends so far that cities hundreds of miles from the eye still experience tropical storm conditions. Hurricanes are measured not just by wind speed, but by their physical diameter, the radius of maximum winds, the extent of tropical storm force winds, the area receiving hurricane force winds. Each measurement reveals a different aspect of the storm's impact zone. Some hurricanes stay compact, with intense winds concentrated near the center. Others spread out, becoming less intense, but affecting much larger areas. Both types are dangerous, just in different ways. The compact storms hit harder. The sprawling storms hit more places. But every hurricane, regardless of size, follows the same basic rules. Warm water feeds them. Cool water weakens them. Wind shear tears them apart. And always, they move at that patient pace across the ocean, taking their time, following paths written by atmospheric physics. As these massive systems move across the ocean, they spin, not randomly, but in perfect spirals. Every hurricane in the northern hemisphere spins counterclockwise. Every one in the southern hemisphere spins clockwise. This isn't coincidence, it's physics. The force behind this spin is called the Coriolis effect. It happens because Earth rotates. As our planet spins eastward, everything on its surface moves at different speeds depending on latitude. The equator moves faster than the poles. This difference in speed affects anything that moves across large distances, including air. Think of it this way. Air flowing toward the center of a low-pressure system wants to move straight, but the ground beneath it is rotating. In the northern hemisphere, this rotation deflects moving air to the right. In the southern hemisphere, it deflects left. This deflection creates the spin. The spiral shape emerges naturally from this process. Air rushes inward toward the low-pressure center. As it moves, the Coriolis effect curves its path. Instead of flowing straight to the middle, it spirals. The closer it gets to the center, the faster it spins. Like water circling a drain, but driven by planetary rotation. Near the equator, the Coriolis effect is too weak to organize hurricanes. That's why these storms never form within about 300 miles of the equator. The rotation isn't strong enough there to create the necessary spin. Hurricanes need that twist to organize their structure. The spiral arms you see in satellite images are rain bands. Long curved lines of thunderstorms wrapping around the center. These bands can stretch for hundreds of miles, each one feeding moisture and energy toward the core. They rotate with the storm, creating that distinctive pinwheel pattern. This pattern appears at every scale. Zooming in on a hurricane reveals smaller spirals within larger ones. Cloud formations spiral. Rain bands spiral. Even the eye wall itself shows spiral structure. Its patterns repeating at different sizes, all driven by the same rotating forces. The tighter the spiral, the stronger the hurricane. When the rain bands wrap closely around the eye, winds accelerate. When the spiral loosens, the storm weakens. Meteorologists read these patterns like a language, understanding the storm's strength and organization from its shape alone. Other planets have similar spirals in their atmospheres. Jupiter's Great Red Spot is essentially a massive hurricane that's lasted for centuries. Saturn has a hexagonal storm at its north pole. These alien weather patterns follow the same rules as Earth's hurricanes, proving these spirals are universal physics in action. The beauty of the spiral isn't accidental. It's the most efficient shape for moving energy from outside to inside. Nature repeatedly creates spirals because they work. Galaxies spiral, seashells spiral, DNA spirals, water spirals down drains, and hurricanes spiral across oceans. Every time you see a hurricane from above, you're watching Earth's rotation made visible. The planet's spin translated into cloud patterns. It's one of the few ways we can actually see our world turning, written in wind and water vapor across thousands of miles of atmosphere. The spiral is Earth signing its name on the weather. Behind every spiral, every spin, every organized pattern sits one simple requirement: warm water. Without it, hurricanes cannot exist. The magic number is 80 degrees Fahrenheit. Ocean surface temperature must reach at least this threshold for a hurricane to form. Below 80 degrees, the water doesn't provide enough energy. Above it, the ocean becomes fuel. Here's how the energy transfer works. Warm water evaporates easily. When tropical sunshine heats the ocean to 80 degrees or higher, water molecules escape from the surface into the air above. This process is evaporation, and it carries heat with it. The water vapor rising into the atmosphere holds enormous amounts of energy. When that vapor condenses back into liquid water, droplets high in the storm clouds, it releases all that stored heat. This release warms the surrounding air, causing it to rise faster. More air rushes in below to replace it. More water evaporates. More heat rises. The cycle accelerates. Think of the ocean as a battery storing solar energy in the form of heat. The hurricane is the circuit connecting that battery to the atmosphere. As long as the battery stays charged above 80 degrees, the storm can draw power from it. This explains why hurricanes form in specific places, the tropics and subtropics during summer and early fall. These are the only times and places where ocean temperatures consistently exceed 80 degrees across large areas. The Caribbean, the Gulf of Mexico, the tropical Atlantic and Pacific. Warm water zones. It also explains why hurricanes die when they move over cooler water or make landfall. Cut off from their energy source, they starve. A hurricane traveling north into cooler Atlantic waters weakens rapidly. The water temperature drops below 80 degrees. Evaporation slows and the fuel supply ends. The depth of warm water matters too. A hurricane doesn't just skim heat from the surface. Its powerful winds churn the ocean, mixing surface water with deeper layers. If warm water extends down 100 feet or more, the hurricane can sustain itself even as it stirs up the sea. If only the top layer is warm with cold water below, mixing brings that cold water to the surface and weakens the storm. Scientists measure something called ocean heat content. It's not just surface temperature, but the total heat stored in the upper ocean. High heat content can intensify hurricanes quickly. The storm taps into a deep reservoir of energy, sometimes strengthening from a weak tropical storm to a major hurricane in less than 24 hours. Climate change is warming the oceans. Average sea surface temperatures have risen about 1 degree Fahrenheit over the past century. This might seem small, but it means more ocean area now exceeds that critical 80-degree threshold. Warm water extends farther north and lasts later into the season. The hurricane fuel zone is expanding, but the fundamental process remains unchanged. Warm water evaporates, vapor rises and condenses. Heat releases into the atmosphere. Air pressure drops. Winds accelerate. The storm organizes itself around this energy flow. Every hurricane, past and present, runs on this same simple fuel. Sunlight captured by the ocean, stored as heat, and released through the elegant machinery of a spinning storm. These storms, powered by warm ocean energy, have terrified and fascinated humans for centuries. And for just as long, we've tried to name them. The word hurricane itself comes from the Caribbean. The Taino people, who lived on Caribbean islands before European contact, worshipped a god of storms named Huracan. Spanish colonists adopted this word, and it spread through European languages, a god's name becoming the term for nature's fury. For most of history, hurricanes had no individual names. They were identified by the places they hit or the dates they struck. The Great Hurricane of 1780, the Galveston Hurricane of 1900. Simple descriptions that blurred together in memory and records. Then, in the early 20th century, an Australian meteorologist named Clement Wragg started giving storms women's names. He chose names of politicians he disliked, using weather forecasts as subtle insults. The practice didn't catch on immediately, but the idea stuck. During World War II, military meteorologists tracking Pacific typhoons began using women's names systematically. It was easier than coordinates or technical designations. Pilots and sailors could remember names. The system worked. By 1953, the United States officially adopted alphabetical women's names for Atlantic hurricanes: Alice, Barbara, Carol, Dolly. Each storm got the next name on the list when the alphabet ran out. The cycle started over the following year. This continued until 1979, when men's names were added. The change came after years of criticism that using only women's names for destructive storms was sexist. Now the lists alternate. A male name, then female, then male again. Alex, Bonnie, Colin, Danielle. Today, the World Meteorological Organization maintains 6 rotating lists of names for Atlantic hurricanes. Each list has 21 names, used once every 6 years. When you hear about Hurricane Maria, it's using a name from a list that will cycle back around in 2029. Some names never return. When a hurricane causes exceptional destruction or death, its name is retired. Katrina will never name another storm. Neither will Harvey, Irma, or Michael. These names become permanent markers of specific disasters, removed from rotation out of respect. The naming system now covers all tropical cyclone basins worldwide. The Atlantic and Eastern Pacific use English names. The Western Pacific uses names submitted by various Asian countries, including flowers, animals, and celestial objects. The Indian Ocean has its own list. Each region maintains its tradition. Names serve a practical purpose beyond memory. When multiple storms exist simultaneously in the same ocean basin, names prevent confusion. In 2020, 5 named storms were active at once in the Atlantic. Without names, tracking them would be chaos. The alphabetical system also reveals season intensity at a glance. A storm named with an early letter formed early in the season. Late alphabet names indicate an active year. When forecasters reach names starting with W, it means the season has been exceptionally busy. In 2005, the Atlantic ran through all 21 predetermined names and had to use Greek letters for additional storms. Alpha, Beta, Beta, Gamma. It happened again in 2020. Both years set records for named storm activity, but whether named after gods, politicians, or simply assigned from an alphabetical list, the storms themselves remain unchanged. There's still water and wind following physical laws. The names are human constructs, our attempt to organize and understand forces far larger than ourselves. Beyond names, we classify hurricanes by their power. This system helps us understand what each storm can do. In 1971, civil engineer Herbert Saffer and meteorologist Robert Simpson created a 5-category scale. It measures hurricanes by their sustained wind speeds. Category 1 is the weakest. Category 5 is the strongest. The scale is simple but effective. Category 1 hurricanes have winds between 74 and 95 miles per hour. These are the least intense hurricanes, but they're still dangerous. They can damage roofs, snap tree branches, and cause power outages. The wind is strong enough to turn loose objects into projectiles. Category 2 brings winds from 96 to 110 miles per hour. Now we see more significant damage. Roofs can lose shingles or sections. Trees with shallow roots topple over. Power outages last days instead of hours. Mobile homes face serious risk. Category 3 marks the beginning of major hurricanes. Winds reach 111 to 129 miles per hour. Well-built homes sustain major damage. Large trees snap or uproot. Electricity and water may be unavailable for weeks after the storm passes. This is where evacuations become critical. Category 4. Hurricanes pack winds from 130 to 156 miles per hour. Catastrophic damage occurs. Roofs and exterior walls fail even on well-built structures. Most trees snap or uproot. Power poles come down. The area becomes uninhabitable for weeks or months. These storms are rare but devastating. Category 5 represents the peak of hurricane intensity. Sustained winds exceed 157 miles per hour. Some Category 5 hurricanes have recorded winds over 180 miles per hour. At this level, a high percentage of homes will be destroyed. Fallen trees and power poles isolate residential areas. Most of the area becomes uninhabitable for weeks or months. The scale focuses only on wind speed. It doesn't measure storm surge, rainfall, or size. This is both a strength and a weakness. Wind speed is easy to measure and communicate, but some Category 2 hurricanes cause more damage than Category 4 storms because of flooding rather than wind. Hurricane Harvey in 2017 made landfall as a Category 4, but caused catastrophic damage, primarily through rainfall. It stalled over Houston and dropped more than 60 inches of rain in some areas. The wind category didn't tell the full story. Similarly, Hurricane Sandy in 2012 was only a Category 1 at landfall, but caused massive destruction through storm surge and its enormous size. The category system didn't capture its true impact. Despite these limitations, the Saffir-Simpson scale remains the standard. People understand categories. Emergency managers use them to make evacuation decisions. The media reports them. Everyone knows Category 5 means extreme danger. The scale also helps compare storms across time. When someone says Hurricane Camille was a Category 5 in 1969, we immediately understand its intensity matched recent monsters like Katrina, Michael, or Dorian. The categories create a common language, but ultimately, every hurricane is unique. 2 Category 3 storms can behave completely differently. One might be compact with a small wind field. Another might sprawl across hundreds of miles. The category tells part of the story, but never all of it. Wind speed matters, but so do size, forward motion, rainfall, and storm surge. The number is a guide, not a complete description. These categorized storms don't arrive randomly throughout the year. They follow a calendar, a season with clear beginning and end. In the Atlantic Ocean, hurricane season officially runs from June 1st through November the 30th, 6 months when conditions align to create these massive storms. Outside this window, Atlantic hurricanes are extremely rare. The ocean simply isn't warm enough. The season peaks in early September, specifically around September 10th. This is when ocean temperatures reach their highest, wind shear drops to its lowest, and atmospheric conditions become most favorable. If you plot hurricane frequency on a graph, it rises through summer, spikes sharply in September, then falls through October and November. June sees few hurricanes. The ocean is still warming from winter. Water temperatures hover around that critical 80-degree mark in only limited areas. Early season storms tend to form in the Gulf of Mexico or Western Caribbean, where water warms fastest. July and August bring increasing activity as more ocean area exceeds 80 degrees. But wind shear from the jet stream often remains strong enough to tear apart developing storms. These months produce hurricanes, but not as many as you might expect, given the warm water. Then comes September. The ocean has reached maximum warmth. The jet stream retreats northward, reducing wind shear. African easterly waves, clusters of thunderstorms moving west from the African coast, become more organized. All factors align. September produces more hurricanes than any other month. October remains active, though cooling begins. Water temperatures start dropping in the northern Atlantic, but stay warm in the Caribbean and Gulf. Late-season storms often form closer to land rather than out in the open ocean. They can still reach major intensity. November marks the season's end. Only the southernmost waters remain warm enough. Late November, hurricanes are unusual but not impossible. A few memorable storms have formed even in December, though these are outliers breaking the normal pattern. This seasonal rhythm has persisted for as long as we've kept records. Ancient sailors in the Caribbean learned to avoid hurricane months. Colonial settlements planned around the season. Modern cruise lines still adjust routes based on this calendar. Other ocean basins have different seasons. The Eastern Pacific hurricane season runs from May 15th through November the 30th, starting earlier because that ocean warms faster. The Western Pacific has no formal season. Typhoons can form year-round in those consistently warm waters, though they're more common in summer and fall. The Southern Hemisphere's season runs opposite the Northern Hemisphere, November through April. When it's winter in the North Atlantic and hurricanes are impossible there, it's summer south of the equator and cyclones spin over the Indian Ocean and South Pacific. This global pattern reflects Earth's tilt and the journey of direct sunlight. As the sun's most direct rays move north in Northern Hemisphere summer, they heat northern tropical oceans. 6 months later, when those rays move south, southern oceans warm and northern ones cool. The predictability helps. We know when to watch, when to prepare, when to relax. Hurricane forecasters can plan their schedules. Coastal residents know which months demand attention. The season has rhythm, and that rhythm brings a measure of certainty to something otherwise chaotic and powerful. Within this predictable season, each hurricane creates something invisible but measurable: a drop in air pressure. Air pressure is the weight of atmosphere pressing down on everything. At sea level, this pressure averages about 1,013 millibars. That's normal atmospheric weight. We don't feel it because we're adapted to it, but it's always there, pushing down from above. When a hurricane forms, pressure at its center drops, sometimes dramatically. The stronger the hurricane, the lower the pressure. Category 5 hurricanes can have central pressures below 900 millibars. That's more than 100 millibars below normal. The atmosphere above the storm weighs significantly less. This pressure difference drives everything about hurricanes. Air naturally flows from high pressure to low pressure, trying to equalize. The greater the pressure difference, the faster air moves. A hurricane's low pressure center acts like a vacuum, sucking air inward from all directions. That inward rushing air is the hurricane's wind. The tighter the pressure gradient, the difference in pressure over distance, the stronger the winds. A hurricane with a very low central pressure and normal pressure, just a few miles away, will have extremely violent winds. The air is desperate to fill that low pressure void. Meteorologists use pressure readings to estimate hurricane intensity. Often, pressure is a better indicator than wind speed. Pressure can be measured accurately by aircraft flying into the storm or by drop sondes, instruments parachuted into the eye. Wind speed is harder to measure consistently, especially at the surface where it matters most. The lowest pressure ever recorded in an Atlantic hurricane was 882 millibars in Hurricane Wilma in 2005. That's 131 millibars below normal, an enormous atmospheric deficit. The winds in Wilma's eye wall exceeded 180 miles per hour. In the Pacific, Typhoon Tip in 1979 set the all-time record at 870 millibars. The storm's eye was 40 miles wide. Its wind field extended over 1,000 miles in diameter. The low pressure had created a monster. The relationship between pressure and wind isn't perfectly linear, but it's close enough. Generally, every 1 millibar drop in pressure corresponds to about 1 mile per hour increase in wind speed. A hurricane with 950 millibars might have winds around 80 miles per hour. One at 920 millibars might reach 120 miles per hour. This pressure drop affects more than just wind. It raises sea level beneath the storm. Lower atmospheric pressure means less weight pushing down on the ocean surface. The water rises, sometimes by several feet, creating part of the storm surge that floods coastlines. Barometers measure atmospheric pressure. Before modern forecasting, sailors watched their barometers obsessively. A rapidly falling barometer meant a storm was approaching. The faster it fell, the more intense the storm. A barometer dropping below 29 inches of mercury, about 980 millibars, signaled serious danger. Today, hurricane hunter aircraft measure pressure by flying directly into the eye. They drop instruments that radio back data as they fall. Every pressure reading helps forecasters understand the storm's current strength and predict its evolution. The invisible weight of air becomes numbers on screens, translating atmospheric physics into actionable information about these powerful systems spinning across warm water. That low pressure center doesn't just create wind, it creates rain. Massive amounts of rain. Hurricanes are among the most efficient rain-producing machines in nature. A single storm can drop trillions of gallons of water. The rainfall is so intense, so prolonged, that it reshapes the landscape beneath it. The process starts with evaporation. Warm ocean water turns to vapor and rises into the storm. As this vapor-laden air spirals upward, it cools. Cool air cannot hold as much moisture as warm air. The excess water condenses into droplets, forming clouds and releasing heat that powers the storm further. These droplets grow, they collide and merge. When they become heavy enough, they fall as rain. But in a hurricane's powerful updrafts, many droplets get swept back up before reaching the surface. They cycle through the storm multiple times, growing larger with each pass, until finally falling as heavy rain. The rain bands circling a hurricane can produce rainfall rates of several inches per hour. When these bands stall over one location, the accumulation becomes staggering. Hurricane Harvey dropped over 60 inches of rain on parts of Texas in 2017. 5 feet of water falling from the sky. This water delivery has ecological importance. Many regions depend on hurricane rainfall to replenish reservoirs and groundwater. In drought-prone areas, a hurricane's rain can be a blessing despite the storm's other impacts. The water feeds rivers, fills lakes, and soaks deep into aquifers. Taiwan receives significant water supply from typhoons each year. Without these storms, the island would face severe water shortages. The same is true for parts of Mexico, Central America, and the Caribbean. Hurricane rain is built into the regional water cycle. Even in the United States, hurricane remnants often bring beneficial rain to inland areas. As weakened tropical systems move inland and interact with fronts, they can drop moderate sustained rain across multiple states. This water is gentler than the torrential coastal downpours, spreading more evenly across farmland and forests. The flooding potential is real and dangerous, but the water itself is fresh. It's distilled by the evaporation process. Ocean salt stays behind when water evaporates. What falls as rain is pure fresh water, chemically identical to rain from any other weather system. Some hurricanes produce more rain than others. Slow-moving storms drop more water because they linger over the same area. Hurricane Florence in 2018 crawled across the Carolinas at just 2 miles per hour, dumping up to 30 inches of rain. Fast-moving storms spread their rainfall over larger areas, but accumulate less in any one spot. The total water volume is almost incomprehensible. Hurricane Harvey released an estimated 27 trillion gallons of rain over Texas and Louisiana. If you spread that water evenly across Texas, the entire state would be covered in about 5 inches. One storm, 27 trillion gallons. This makes hurricanes crucial components of Earth's water cycle. They transport water from ocean to land, from tropical regions toward higher latitudes. They redistribute moisture across the planet. Without tropical cyclones, the global water balance would shift. Some areas would receive less rain. Ocean evaporation would accumulate differently. So while we focus on wind speed and categories, hurricanes are fundamentally water systems. They're atmospheric rivers, carrying ocean moisture inland and releasing it as rain that feeds ecosystems, fills reservoirs, and shapes the hydrology of entire regions. All that water, all that organized energy, all that power can be torn apart by something invisible. Wind shear. Wind shear is the change in wind speed or direction with height. In simple terms, when winds blow one direction at the surface and a different direction several miles up, that's wind shear. This difference in wind flow can rip a hurricane to pieces. Hurricanes need vertical alignment to survive. The rising air at the surface, the circulation aloft, and the descending air at the edges must all work together in one cohesive column. The storm is a unified system from ocean surface to upper atmosphere. When wind shear disrupts this alignment, the system falls apart. Imagine building a tower of blocks. If you push the top blocks one direction while holding the bottom blocks in place, the tower topples. Wind shear does exactly this to hurricanes. Upper-level winds blow the top of the storm in one direction, while surface winds go another way. The storm tilts, stretches, and eventually breaks. Strong wind shear tilts the hurricane's core. The eye becomes asymmetric. Rain bands on one side of the storm are torn away from the center. The organized circulation weakens. Instead of a tight spiral, the storm becomes disorganized, its energy scattered across the atmosphere. This is nature's hurricane suppression system. Wind shear acts like a natural defense, preventing every tropical disturbance from becoming a monster. Most tropical waves emerging from Africa encounter enough shear to prevent development. Only when shear is weak do hurricanes strengthen. The jet stream creates significant wind shear. This river of fast-moving air flows through the upper atmosphere, typically across the middle latitudes. When the jet stream dips southward, it brings strong upper-level winds over tropical regions. These winds shear apart developing storms. In El Niño years, the jet stream shifts. It flows more strongly across the tropical Atlantic and eastern Pacific. This increased shear suppresses Atlantic hurricane formation, while sometimes favoring eastern Pacific storms. The global wind patterns shuffle, changing where hurricanes can develop. La Niña creates opposite conditions. The jet stream pulls northward. Wind shear decreases across the Atlantic. Hurricanes form more easily and intensify more readily. La Niña years typically see more Atlantic hurricane activity. Wind shear also affects existing hurricanes. A storm can be intensifying over warm water when sudden wind shear arrives. Within hours, the hurricane weakens. Satellite images show the eye becoming ragged. Rain wraps around only one side. The storm fights to maintain structure, but loses. Some resilient hurricanes survive moderate shear. They tilt, but don't collapse. The low-level circulation continues even as upper winds try to separate it from the higher atmosphere. These storms often wobble, their strength fluctuating as they battle the hostile wind environment. Meteorologists monitor wind shear closely when forecasting hurricane intensity. Even perfect ocean temperatures won't help a storm strengthen if wind shear is strong. The forecast models calculate shear values throughout the atmosphere, predicting whether conditions favor intensification or weakening. Wind shear is measured in knots per vertical distance. Shear below 10 knots is considered low, favorable for hurricane development. Shear above 20 knots typically prevents strengthening or causes weakening. Between 10 and 20 knots, the outcome depends on other factors like ocean heat and the storm's existing structure. So while we often focus on what creates and strengthens hurricanes, wind shear reminds us that the atmosphere has built-in limitations. Not every warm ocean breeds a monster. The vertical wind environment acts as gatekeeper, allowing only some storms to reach their full potential. Throughout history, some hurricanes have survived all natural defenses and grown into legendary storms. These giants changed coastlines, altered human settlements, and taught us about nature's power. The Great Hurricane of 1780 remains the deadliest Atlantic hurricane on record. It struck the Caribbean islands in October, killing over 20,000 people. The storm destroyed entire fleets of British, French, and Spanish naval vessels. Ships sank with all hands. Coastal towns vanished. The hurricane influenced the American Revolutionary War by eliminating military forces that might have reinforced British positions. In 1900, a hurricane struck Galveston, Texas, without warning. No satellites existed to track it. No advanced forecasts warned the city. The storm surge submerged the island, killing between 6,000 and 12,000 people. It remains the deadliest natural disaster in United States history. Galveston built a seawall afterward and raised the entire city's elevation, literally lifting buildings and pumping sand underneath. The Labor Day hurricane of 1935 hit the Florida Keys as the most intense hurricane ever to make United States landfall. Wind speeds likely exceeded 200 miles per hour. The barometric pressure dropped to 892 millibars. A work train sent to evacuate workers from the Keys was blown off the tracks. Over 400 people died. The storm was small, but incredibly powerful, like a spinning blade crossing the islands. Hurricane Camille in 1969 devastated the Mississippi coast with winds over 190 miles per hour and a storm surge reaching 24 feet. The surge pushed water 3 blocks inland. Entire neighborhoods disappeared. But Camille also demonstrated how hurricanes weaken inland. After crossing the coast, it rapidly lost strength, eventually causing catastrophic flooding in Virginia from rainfall rather than wind. Hurricane Andrew in 1992 changed how we build in hurricane zones. It carved a path of destruction across southern Florida, destroying over 60,000 homes. The storm revealed that building codes weren't strict enough. Many structures failed, not from extraordinary forces, but from inadequate construction. Florida rewrote its building codes completely after Andrew. Modern homes must withstand much higher wind loads. Katrina in 2005 showed the danger of storm surge in vulnerable coastal geography. The storm itself wasn't the strongest, but New Orleans sits below sea level, protected by levees. When those levees failed, the city flooded. Over 1,800 people died. The disaster was as much about infrastructure and emergency response as it was about the hurricane itself. More recently, Hurricane Maria devastated Puerto Rico in 2017. The storm destroyed the electrical grid completely. Some areas went months without power. The official death toll reached nearly 3,000 when counting deaths from lack of medical care, clean water, and electricity in the storm's aftermath. These storms share common threads. They all encountered favorable conditions that allowed them to reach extreme intensity. They all struck vulnerable populations, and they all taught lessons that changed how we prepare for future hurricanes. But they're also reminders that hurricanes are natural phenomena, not malicious forces. They follow physical laws. They exist because Earth's atmosphere must balance heat. Understanding them removes some of their terror. They're powerful, yes. Dangerous, absolutely. But they're also predictable, comprehensible, and increasingly survivable as our knowledge grows. That growing knowledge comes largely from one technology: satellites. Before 1960, we didn't know hurricanes existed until they were close to land or encountered by ships. Storms could develop and intensify in the open ocean completely undetected. The 1900 Galveston hurricane arrived with minimal warning because nobody knew it was coming until it was too late. The first weather satellite, TIROS-1, launched in April 1960. It carried a television camera that photographed clouds from space. For the first time, meteorologists could see entire weather systems at once. That September, TIROS spotted Hurricane Donna crossing the Atlantic. They watched its every move from formation to dissipation. This changed everything. Suddenly, no hurricane could hide. Every tropical disturbance became visible the moment it organized. Forecasters could track storms across their entire lifespan, watching them strengthen or weaken, turn or maintain course. Modern weather satellites sit in two types of orbits. Geostationary satellites hover over one spot on the equator, rotating with Earth. They provide constant view of the same region, taking images every few minutes. GOES satellites, operated by NOAA, watch the Atlantic and Pacific continuously. Polar orbiting satellites circle Earth from north to south, passing over the poles every orbit. They cover the entire planet, but only see any given spot a few times per day. These satellites carry instruments that measure temperature, humidity, and wind through the atmosphere's depth. Together, these satellites create complete coverage. A hurricane forming anywhere on Earth is spotted within hours. Forecasters track it with images updated every few minutes. They see the eye develop, watch rain bands spiral, and observe the storm structure evolve in real time. Satellites don't just take pictures in visible light. Infrared sensors measure temperature. The coldest cloud tops appear brightest, indicating the most powerful convection. Water vapor channels show moisture distribution through the atmosphere. Microwave sensors peer through clouds to measure rainfall rates and wind speeds. Hurricane hunters still fly into storms, dropping instruments and measuring conditions directly. But satellites provide context those aircraft cannot. The birds see the forest, not just the trees. They reveal how the hurricane fits into larger atmospheric patterns, where it's drawing energy, and how surrounding conditions might affect its path. The resolution keeps improving. Early satellites saw hurricanes as fuzzy, white blobs. Modern satellites resolve individual thunderstorms within the rain bands. They capture eye wall replacement cycles, moments when a hurricane's inner eye wall collapses and a new one forms farther out, temporarily weakening the storm. This visibility transforms forecasting. Meteorologists input satellite data into computer models that simulate the atmosphere's physics. The models run forward in time, predicting where the hurricane will move and how strong it will become. Forecasts now extend 5 days with reasonable accuracy, sometimes 7 days. Compare this to 1900. No satellites, no computers, no 5-day forecasts. Just barometers showing pressure drops and experience suggesting something was coming. Now we watch hurricanes birth over Africa, track them across the entire Atlantic, and predict their landfall location days in advance. Satellites made hurricanes visible. They transformed these storms from mysterious terrors into monitored weather phenomena. The storms haven't changed, but our ability to see them has revolutionized completely. We watch them from space, understanding their every move, no longer caught by surprise. Those satellites watch something remarkable happen when hurricanes reach land. They begin to die. Landfall is the moment a hurricane's eye crosses the coastline. It's the transition from ocean to land, from fuel source to starvation. The change happens quickly. Remember that hurricanes need warm ocean water to survive. They're heat engines converting ocean warmth into atmospheric motion. When the eye moves over land, that heat source vanishes. The storm still has momentum, still has rotation, but it's no longer being fed. Within hours, wind speeds drop. A Category 4 hurricane making landfall can weaken to Category 2 or 1 within 6 hours over land. By 12 hours, it might be a tropical storm. By 24 hours, sometimes just a tropical depression or remnant low pressure system. The weakening follows a pattern. First, the eye fills in. Without warm water rising through the center, the clear eye becomes cloudy. The eye wall, that ring of maximum winds, starts to fall apart. Rain bands lose their organization. The tight spiral becomes ragged and asymmetric. Friction also plays a role. The ocean surface is smooth. Wind flows over it with minimal resistance. Land has trees, buildings, hills, and valleys. All this surface roughness slows the wind. The hurricane's circulation encounters drag it never faced over water. The low-level winds slow, disrupting the entire system. But hurricanes don't disappear instantly. Even weakened, they can travel hundreds of miles inland. Hurricane Camille crossed the Gulf Coast in 1969 and made it to Virginia before dissipating. Its remnants dumped catastrophic rain on the Appalachian Mountains. Hurricane Katrina's remnants reached the Great Lakes. The rainfall continues long after the winds die. Sometimes it intensifies. As the hurricane weakens and slows, its rain bands stall over one area. Without the organized circulation, the system dumps moisture more randomly, but sometimes more heavily in spots. Mountains enhance this effect. When hurricane remnants encounter mountains, the terrain forces air upward. Rising air cools and condenses, creating more rain. The western slopes of mountains often see extreme rainfall from dying hurricanes, causing floods and mudslides. Some hurricanes cross narrow land areas and re-emerge over warm water. They can re-intensify. Hurricane Ivan in 2004 crossed Florida into the Gulf of Mexico. Over the warm Gulf water, it strengthened again before making a second landfall. The storm essentially had two lives because it found new fuel. Occasionally, a hurricane crosses from the Atlantic into the eastern Pacific or vice versa. These crossings are rare and require specific geography. The storm must cross Central America at its narrowest point. Most hurricanes that attempt this dissipate over the mountains, but a few maintain enough circulation to regenerate on the other side as new storms. The transformation from hurricane to remnant low can take days. The system becomes a swirl of rain and clouds, no longer organized enough to be called a tropical cyclone, but still producing weather. These remnants can bring beneficial rain to drought-stricken areas or merge with frontal systems to create powerful mid-latitude storms. Landfall is both ending and transformation. The hurricane as a tropical system dies, but its energy redistributes into other weather patterns. The moisture it carried continues inland. The atmospheric disturbance it created ripples through weather systems for days afterward. The storm changes form, but doesn't simply vanish. Knowing hurricanes weaken over land is one thing. Predicting exactly where they'll make landfall is another challenge entirely. Hurricane forecasting combines satellite data, computer models, historical patterns, and atmospheric physics. It's one of the most complex prediction challenges in meteorology. The process starts with current conditions. Satellites provide the hurricane's exact position, size, and intensity. Weather balloons and aircraft measure temperature, humidity, and wind throughout the atmosphere. Ocean buoys report sea surface temperatures and wave heights. All this data feeds into computers. Forecast models are essentially mathematical simulations of Earth's atmosphere. They divide the atmosphere into a three-dimensional grid of boxes. Each box contains values for temperature, pressure, humidity, and wind. The computer calculates how these values change over time using physics equations. Multiple models run simultaneously. The American GFS model, the European ECMF model, regional models like HWRF that focus specifically on hurricanes. Each model uses slightly different physics equations and grid spacing. They don't always agree. The models predict steering currents. High pressure systems push hurricanes one direction. Low pressure systems pull them another. The jet stream influences upper level flow. All these factors combine to determine the hurricane's path. Track forecasts have improved dramatically. In the 1990s, a 3-day forecast might be off by over 200 miles. Today, 3-day forecasts average about 70 miles of error. 5-day forecasts now are as accurate as 3-day forecasts were 20 years ago. Intensity forecasting remains harder. Predicting whether a hurricane will strengthen or weaken is less reliable than predicting its path. Small changes in ocean temperature, wind shear, or internal storm structure can cause rapid intensification or weakening that models struggle to capture. Rapid intensification is particularly challenging. Sometimes a hurricane strengthens from Category 1 to Category 4 in less than 24 hours. The models might hint at strengthening, but often underpredict how quickly it happens. Hurricane Michael in 2018 rapidly intensified just before landfall, catching some people unprepared. Forecasters don't rely on one model. They examine all available models, looking for consensus. When most models agree on a track, confidence is high. when models diverge, showing different potential paths, uncertainty increases. The forecast cone, that shape showing possible storm locations, widens when uncertainty is higher. The cone doesn't show the hurricane's exact path. It shows where the center might be, with 60 to 70% confidence. The actual storm is much larger than the cone. Areas outside the cone can still experience significant impacts. Ensemble forecasting runs the same model multiple times with slightly different starting conditions. This accounts for measurement uncertainty. If all ensemble members show similar outcomes, the forecast is reliable. If they spread widely, confidence drops. Forecasters update predictions every 6 hours as new data arrives. The hurricane's actual movement gets incorporated. Models rerun with fresh information. Forecasts evolve, sometimes shifting significantly as conditions change. The goal is giving people time to prepare. A 5-day forecast allows coastal evacuations. A 3-day forecast helps businesses secure property. A 24-hour forecast triggers emergency protocols. Each update refines the picture, narrowing uncertainty as the storm approaches. Perfect forecasts remain impossible. The atmosphere is chaotic. Small differences in initial conditions can produce large differences in outcomes. But modern forecasting gives us remarkable warning, turning hurricanes from surprises into anticipated events we can prepare for days in advance. One thing those forecasts must predict is storm surge. It's often the deadliest part of a hurricane. Storm surge is ocean water pushed towards shore by hurricane winds and low pressure. The water rises above normal tide levels, sometimes by 20 feet or more. It floods coastal areas, sometimes miles inland. The process starts with wind. Hurricane winds blow toward shore for hours or days before landfall. This sustained wind pushes surface water ahead of it. The water piles up along the coast like water pushed to one end of a bathtub. The stronger the winds, the higher the surge. But wind speed alone doesn't determine surge height. The storm's size matters more. A large hurricane with a broad wind field pushes more water than a small, intense hurricane. Hurricane Ike in 2008 was only Category 2 at landfall, but produced a surge over 15 feet because of its enormous size. The shape of the coastline affects surge height dramatically. Bays and inlets funnel water into confined spaces. As water crowds into these narrowing areas, it rises higher. Galveston Bay, Tampa Bay, and Chesapeake Bay are all vulnerable to extreme surge because their geometry amplifies the water rise. The offshore continental shelf also matters. A shallow, gradual shelf allows surge to build higher. Water pushed across miles of shallow ocean accumulates, creating a dome of elevated water. A steep shelf drops quickly to deep ocean, giving surge less opportunity to build. Low pressure contributes too. Remember how hurricanes have abnormally low central pressure. This reduced atmospheric weight allows the ocean surface to rise, like the water climbing up a straw when you suck air out. Every 1 millibar drop in pressure raises sea level by about 1 centimeter. In a major hurricane with 900 millibars, that's over a meter of rise, just from pressure. Storm surge arrives before the eye. The strongest surge occurs in the right front quadrant of the hurricane, where you're in the northern hemisphere. In this area, the hurricane's forward motion adds to its rotational winds, creating the strongest push. The left side experiences offshore winds that can actually lower water levels temporarily. The surge arrives like a gradually rising tide, not a wall of water or tsunami. Water levels climb over hours. What was dry beach becomes ankle deep, then knee deep, then waist deep. By the time people realize the danger, roads are flooded and escape becomes impossible. When surge combines with high tide, the flooding gets worse. Forecasters try to predict whether landfall will coincide with high or low tide. The difference can be several feet of additional water. After the storm passes, the surge retreats. The water flows back to sea, sometimes creating strong currents that sweep debris, and unfortunately, sometimes people back toward the ocean. This retreat can be as dangerous as the initial surge. Storm surge killed most people in the 1900 Galveston hurricane. It drowned thousands in Hurricane Katrina when levees failed. Even in recent hurricanes, surge causes more deaths than wind. It's the silent killer, rising water that gives little warning once it begins. Modern forecasting predicts surge reasonably well, but it depends on accurately forecasting the hurricane's track, intensity, size, and forward speed. Small changes in any factor can mean feet of difference in surge height. Beyond the surge, beyond the eye, hurricanes have another distinctive feature: rain bands. These are long curved lines of thunderstorms, spiraling outward from the center. They look like arms reaching out from the hurricane's core. Each band can stretch for hundreds of miles, bringing heavy rain and gusty winds to areas far from the eye. Rain bands form because of how air flows into the hurricane. Air doesn't spiral straight into the center. It converges along curved paths, creating zones where air rises rapidly. Where air rises and cools, clouds form and rain falls. These zones of rising air organize into bands that wrap around the storm. Think of rain bands as miniature fronts within the hurricane. Each one has its own circulation. Air flows into the band from both sides, converges and rises. The rising air creates towering thunderstorms. These storms produce intense rain for 30 to 60 minutes as the band passes, then clear briefly before the next band arrives. The spacing between bands varies. Sometimes they're tightly packed near the center. Other times, they spread out with gaps of 50 miles or more. The number of bands also varies. Some hurricanes have 3 or 4 distinct bands. Others have 10 or more. The outer rain bands arrive first, sometimes a full day before the eye. People experience periodic bursts of heavy rain and wind, separated by calmer periods. This creates a false sense that the storm is passing. But it's just the outer bands. The worst weather is still approaching. Rain bands rotate with the hurricane. They're not stationary. A band that passes over one location moves on, but the next band behind it follows the same path hours later. This creates a repeating cycle of rain and relative calm. Tornadoes can form in rain bands. The bands contain wind shear and instability, perfect conditions for tornado development. Hurricane-spawned tornadoes are usually weak, but can cause significant localized damage. The right front quadrant of the hurricane produces the most tornadoes, the same area that experiences the strongest surge. The inner rain bands, closest to the eye, contain the heaviest rain. They feed moisture directly into the eye wall. As air spirals inward through these bands, it picks up more water vapor from the ocean surface. By the time it reaches the eye wall, it's laden with moisture, ready to condense into torrential rain. Sometimes rain bands organize into secondary eye walls. A ring of intense thunderstorms forms outside the primary eye wall. If this ring strengthens enough, it can choke off the inner eye wall, causing the original eye to collapse. The storm temporarily weakens during this eye wall replacement cycle. Then, the new outer eye wall contracts, and the hurricane re-intensifies. Forecasters use rain band structure to assess hurricane health. Well-organized, tightly wrapped rain bands indicate a strong, intensifying storm. Asymmetric or broken bands suggest weakening or wind shear damage. The bands tell a story about the storm's internal dynamics. Rain bands also determine flooding patterns. Areas hit by multiple bands accumulate significantly more rain than areas between bands. The spacing and speed of band movement influence whether rainfall overwhelms drainage systems or spreads out enough to be manageable. These spiraling arms of thunderstorms aren't random. They're organized structures, each one a piece of the larger system, all rotating together in the hurricane's grand circulation. These spiraling storms with rain bands and eyes aren't unique to the Atlantic. They form in every tropical ocean basin worldwide. We just call them different names. In the Western Pacific, they're typhoons. Same structure, same physics, same rotating system powered by warm water. The word typhoon likely comes from Chinese taifeng, meaning great wind. The Western Pacific produces more tropical cyclones than any other basin, averaging 25 per year. In the Indian Ocean and South Pacific, they're simply called cyclones. Again, identical in structure to Atlantic hurricanes. The terminology changes, but the meteorology doesn't. All three names describe the same phenomenon. The physics governing these storms is universal. Warm water above 80 degrees, low wind shear, Coriolis effect providing spin, rising air releasing heat. These requirements apply everywhere. A typhoon in the Philippines follows the same rules as a hurricane in the Caribbean. But regional differences exist. Western Pacific typhoons tend to be stronger on average than Atlantic hurricanes. The Pacific Ocean is larger, providing more room for storms to intensify over warm water before hitting land. Some typhoons reach wind speeds over 200 miles per hour. The Indian Ocean has 2 cyclone seasons because of monsoon patterns. The primary season runs April through June and October through December, avoiding the monsoon months when wind shear is too strong. The Bay of Bengal produces particularly destructive cyclones that have killed hundreds of thousands in Bangladesh and India throughout history. The South Pacific and Australian region experiences cyclones from November through April, their warm season. Australian cyclones spin clockwise because they're in the southern hemisphere. The Coriolis effect works in reverse south of the equator. Despite different names, the international meteorological community treats them as one global phenomenon. The generic term is tropical cyclone. Hurricanes, typhoons, and cyclones are all tropical cyclones, named based on where they form. No tropical cyclones form in the South Atlantic or eastern South Pacific. These regions lack the necessary conditions. Water temperatures stay too cool, or wind shear remains too strong, or the Coriolis effect is too weak near the equator. These ocean basins are tropical cyclone deserts. Though in 2004, something extraordinary happened. A tropical cyclone formed in the South Atlantic and hit Brazil. Meteorologists named it Cyclone Catarina. It was the first confirmed South Atlantic tropical cyclone. The conditions that normally prevent formation briefly aligned perfectly, allowing this rare storm to develop. The strongest tropical cyclone ever recorded was Typhoon Tip in 1979. Its central pressure dropped to 870 millibars. Its wind field stretched over 1,000 miles in diameter, half the size of the United States. The storm formed in the Western Pacific and fortunately weakened before making landfall in Japan. Different basins have different naming systems. The Atlantic uses predetermined alphabetical lists. The Western Pacific uses names submitted by member countries, including words like Haiyan, Mangkhut, and Yutu. The Indian Ocean has its own lists. Each region maintains its traditions, while acknowledging these are all the same type of storm. Understanding this global perspective shows how common these storms are. While the Atlantic averages 12 named storms per year, the entire planet produces about 80 tropical cyclones annually. They're a regular feature of Earth's climate system, occurring in multiple ocean basins, redistributing heat and moisture across the globe. Those 80 annual storms worldwide are forming in a changing climate. The oceans are warming. Global sea surface temperatures have risen about 1.5 degrees Fahrenheit over the past century. This might sound small, but it shifts where and when hurricanes can form. Remember that 80-degree threshold. As oceans warm, more water area exceeds this temperature. The zone where hurricanes can develop is expanding northward. Hurricane season starts earlier and lasts longer. Water that was too cool for hurricane formation now supports it. We're also seeing warmer water extending deeper below the surface. This deep ocean heat content matters because hurricanes mix surface water with deeper layers. When deeper water is also warm, the storm maintains its fuel supply even as it churns the ocean. This allows for rapid intensification. Rapid intensification events are increasing. Storms strengthening by 35 miles per hour or more in 24 hours. Hurricane Michael went from Category 2 to Category 5 in about 36 hours over the Gulf of Mexico in 2018. The warm water provided unlimited fuel. Rainfall from hurricanes is also increasing. Warmer air holds more moisture. For every 1 degree Celsius of warming, the atmosphere can hold about 7% more water vapor. When hurricanes form in warmer conditions, they carry more moisture and produce heavier rain. Hurricane Harvey demonstrated this. The storm stalled over Houston and dropped unprecedented rainfall. Climate attribution studies suggest warming made Harvey's rainfall about 15% heavier than it would have been a century ago. That's trillions more gallons of water. However, total hurricane numbers may not be increasing. Some research suggests warming might actually reduce the total count of tropical cyclones globally, but the storms that do form could be more intense on average. Fewer storms, but stronger ones. The relationship is complex because warming affects multiple factors. It warms ocean water, which favors hurricanes, but it also can increase wind shear in some regions, which tears storms apart. The balance between these competing effects varies by location. The Atlantic seems particularly sensitive. Natural cycles like the Atlantic multi-decadal oscillation create periods of more and fewer hurricanes spanning decades. Separating climate change signals from these natural cycles is challenging. Both factors are operating simultaneously. What's clearer is that Category 4 and 5 hurricanes are becoming proportionally more common. The percentage of hurricanes reaching these highest intensities is rising. The strongest storms are getting stronger, even if the total number of storms isn't necessarily increasing. Storm surge risk is also rising because sea levels are higher. The same hurricane today produces more surge than an identical storm would have 50 years ago, simply because it's pushing water onto a higher baseline. Miami, New Orleans, and other coastal cities face increasing surge risk, even if hurricane behavior itself doesn't change. The science continues evolving. Climate models project future changes, but uncertainty remains. Different models show different regional effects. What's consistent across models is that warming will continue affecting hurricane behavior in measurable ways. Understanding this connection doesn't make hurricanes scarier, it makes them more predictable. We're learning how a changing climate alters these storms. This knowledge helps us adapt, prepare better, and build more resilient coastal communities. Hurricanes are natural. They've existed long before humans. But how they behave in a warmer world is something we're actively learning. Step back now and see the bigger picture. Hurricanes aren't disruptions to Earth's climate. They're part of how the planet maintains balance. The equator receives more solar energy than the poles. This creates a heat imbalance. Tropical regions would keep getting hotter, polar regions colder, except Earth has mechanisms to redistribute this heat. Ocean currents move warm water poleward. Atmospheric circulation transfers heat through wind patterns. And hurricanes play their role too. Each hurricane transports enormous amounts of heat from tropical oceans toward higher latitudes. As the storm moves north or south from where it formed, it carries energy with it. When hurricanes dissipate, they release this heat into regions that need it. They're part of Earth's cooling system, moving excess tropical warmth toward cooler areas. Without tropical cyclones, the equatorial regions would retain more heat. The temperature gradient between equator and poles would be sharper. Weather patterns would shift. The planet has evolved with hurricanes as one mechanism for energy distribution, and they serve this function whether we appreciate it or not. This is why hurricanes exist. Not to threaten coastlines or test human resilience, but because physics demands heat move from warm places to cool places. The rotating Earth, warm oceans, and temperature differences create conditions where spinning storms are inevitable. They're solutions to thermodynamic problems written in cloud and wind. Seen this way, hurricanes become less frightening and more fascinating. They're natural consequences of how planets with oceans and atmospheres manage energy. They follow rules. They serve purposes in the larger climate system. They're predictable in their unpredictability. Every year, the cycle repeats. Oceans warm through summer. Tropical waves emerge from Africa. Some intensify into named storms. A few become major hurricanes. They travel their paths, deposit their rain, release their energy, and dissipate. The season ends. The ocean cools. Then months later, it begins again. Humans have learned to coexist with this cycle. We track storms with satellites. We model their paths with supercomputers. We build to withstand their winds. We evacuate when necessary. We've transformed hurricanes from mysterious terrors into managed risks. The storms haven't changed fundamentally in thousands of years. Our understanding has. So, as you settle into sleep tonight, remember those spirals spinning somewhere over warm water. They're not enemies. They're expressions of planetary physics. They're Earth managing its energy budget. They're nature following the laws written into the universe. The warm ocean feeds them. The Coriolis effect spins them. The pressure gradients drive their winds. The moisture condenses into rain. And through it all, heat moves from where there's too much to where there's too little. Balance maintained through swirling storms. If you've enjoyed this peaceful journey through hurricane science, please hit that like button and subscribe to Simple Sleepy Science. We explore fascinating topics every night, transforming complex science into calm bedtime stories. Tomorrow brings another wonder to explore together. What will it be? You'll have to come back and see. Sleep well, friends.